Good evening to all. Welcome to the 21st lecture of the course Experimental Methods in Thermal Engineering. In our previous lecture, we have discussed about thermal anemometry. In today's lecture, we will once again continue our discussion on the measurement of velocity. And in particular, now we will start our discussion on particle-based measurement techniques. Okay. So particle-based measurement techniques, in this type of techniques, what we do, let us consider that if we are having some pipeline and through this pipe the flow of fluid is happening. Okay. So what we will be doing, we will be seeding small number of particles and then we will try to trace their motion. Okay. So depending upon the concentration of the particle and the time resolution at which we are tracing their motion, we can get spatial and temporal evolution of the velocity profile of the flow. Okay, so generally what we are doing, particles are actually taken inside the flow field which follow the flow velocity fluctuations, and these particles are sufficient in number in order to provide desirable spatial and temporal resolution. Okay, so if we consider in comparison to the thermal anemometry we have discussed in our previous lecture, in comparison to that, in this particular technique we will be having more spatial and temporal evolution. Okay, and another advantage over here with the particle based techniques is that in these particular techniques we consider the particles inside our flow field which are of buoyant nature. It means they will be following the flow of the fluid. Okay, so because of that we will not be having any intrusion inside the flow field which will be actually uh, distracting or changing our flow field. Okay, so because of that, this type of measurement is also termed to as non-intrusive measurement of the flow field. Okay, now tracer particles should act as good light scattering centers, because particularly what we have to do while these particles will be flowing inside the flow field, we have to trace their motion. Okay, so for tracing the motion of the particle, majority of the time we go for the optical measurements. Okay, so what basically does, we allow some light to uh, incident on these particles, and then these particles actually scatter the light, and we try to measure some signal based on this scattering of the light. Okay, and that we try to relate with the velocity of the flow field. So that's why particles should have good light scattering centers. And why? Because this will be improving the signal quantity for given incident laser power. Okay, now, flow tracking demands small particles. Why? Because we want that particles should be of buoyant nature. Okay, so that's why the density of particles should match with the density of the flow, density of the fluid, and at the same point of time, our particles should not affect or disturb flow field. So, because of that, flow tracking demands that particles should be of size as small as possible. However, in order to achieve good light scattering characteristics, the size of the particles should be large. Okay, so what we have to do? We have to do some trade-off in between the size and scattering characteristics of the particles, and then based on that, we have to select some optimal particle size. Now, what I have done, I have included over here one governing equation which actually derives the motion of the particle inside the flow field. So, in this particular equation, you can see on the left hand side, we are having nothing but rho p as density of the particle, and this term 4 pi 3 pi a cube refers to the volume of the particle, where a is nothing but radius of the particle, and this dv by dt refers to the acceleration of the particle. Now, this acceleration of the particle will be depending upon large number of factors. So over here we are having some non-inertial forces, then some body forces which will be nothing but the balance of the gravity and the buoyancy forces. Then we will be having some quasi-static viscous force which will be acting on the particle because of the viscosity of the fluid medium. Then we will be having some force which will be acting because of the time history of the particle, and this particular type of force is also referred to as Bassett force. then we will be having some added mass force and some lift force. Lift force is actually particularly relevant to the particles which are actually subjected or placed inside the fluid medium which is subjected to rotation. Okay, and most importantly, this is also relevant to the turbulent motion, because in case of turbulence we are having large number of small eddies where we are having the strong rotational effects inside our flow. So there also lift force actually becomes prominent. So this is a detailed equation. This particular equation is known as Bessel-Bosenic equation, which actually describes the behavior of a spherical solid particle under the conditions of low Reynolds number inside the flow field. Okay. However, while we will be employing the particles, in particularly in the particle based velocity measurement techniques, there the size of particle will be very small. So majority of these forces will be actually negligible, and we will be having lesser number of forces which will be coming into picture. So because of that, we will be getting some simplified relationship in between the particle velocity and the fluid flow velocity. So Vp minus u is nothing but difference between the particle velocity and the velocity of the flow, which is equal to 2 by 9 a square rho p minus rho f divided by mu into dvp by dt. So this is actually equation is nothing but simplified version of the previous equation, and this is particularly applicable for very low size particle. Generally what we do when we are going for the velocimetry using particle based techniques, we have to consider the diameter of the particle in the order of micrometers. Okay, so we will be getting this as simplified relationship. Now in this particular equation, you can see on the left hand side we are having some difference. So this particular difference in between the particle velocity and the flow field velocity is something which is known as slip. Okay, or sometimes it is also known as slip velocity. Okay, so now the basic assumption or the basic condition for using the particle based techniques is that we should have zero slip condition. By meaning of zero slip condition means we are our particle is actually exactly following the motion of the flow field. Okay, so by tracking the particle we can directly relate the motion of the flow field, or we can determine the distribution of the velocity field. Okay, so from here, as I have told you that we should have this difference between Vp minus u is equal to 0. So from here, one important thing you can clearly see that the density difference rho p minus rho f should be equal to 0. Okay, so this tells that we should have density of particle identical to that of the density of the fluid. Okay, so that is something, this assumption is actually very true in case of the flow of liquids. While liquids are flowing, because liquids are having generally high density and it is comparable to that of some of the solids. So this condition is very easy to obtain in case of the flow of liquids. However, if we are having the flow of gas, then obviously we know that particles will be either of solid, or we can take droplets as seeded particle inside the gaseous flow field. So obviously every time what will be happening, we will be having the density difference between the particle to the fluid of the order of 10 to power 3. Okay, because in case of gases we will be having very small density, whereas if we are taking the liquid or solid particle as a buoyant particle inside our flow field, we will be having significant change in significant difference between the density of the gaseous fluid and the density of the particle. So therefore, under such circumstances, what is done, we have to consider very small diameter of the particle, because if we will be considering the particle of very small, particularly in the range of 0.5 micrometer to 5 micrometer, so that will be actually we will be finding that the weight of the particle will be very small and it will be almost acting as buoyant, okay, inside our flow field. Then we may employ the larger particles. So particularly for liquids, that is very easy to employ. However, while we are using for the gases, then also what can be done, we may take actually hollow solid particles. Okay, so by making particle hollow, we can actually decrease their weight and we can make them buoyancy neutral. Okay, and particularly while we are using the liquids, then we may use different type of particles. So for example, you can see over here hollow glass spheres or polyimide particles of relatively larger diameter, which may range from 5 micrometer to 50 micrometer, can be employed while we have to resolve the flow field of liquid. Then this particular table describes the commonly used pressure particles for particularly for the particle image velocimetry. Okay, so what we are having in general, now I have started the discussion on particle based measurements. So where we are seeding some of the particle. Now for tracking the motion of the particle, we may have different techniques. So one of the technique where we take the photographs of the particle, that particular technique is referred to as particle image velocimetry. And then another technique is also there, which is based on the principle of Doppler's effect. That particular method is known as laser Doppler anemometry. Apart from that, we may have molecular tracking velocimetry or Doppler global velocimetry. So different techniques can be employed. But what I'll be doing first, I will give you the uh, description or details of in general particle based methods, and then at the end of this lecture I'll discuss about laser Doppler velocimetry, and then this second technique particle image velocimetry I will discuss in our next lecture. Okay, so in this particular slide what I have included some of the commonly used pressure particles which are used for particle image velocimetry method. Okay, so you can see over here fluids, I have taken air and water. So with air, these are the different particles which can be employed. So you can see with air, we can use even liquid droplets also as our tracer particle. For example, the solution of glycerin and water is included over here, or the droplets of vegetable oils. Okay, and then we are having some TiO2 based solid particles also as tracers. So if you see the corresponding diameter, so we are having the diameter requirement in the order of micrometers, 1, 2, 3, particularly while we are using fluid as air, and this is the corresponding density value of the particles. Then while we are using the water as our fluid medium, with water majority of the time we will be using solids as our tracer particles, and you can see the corresponding diameter of the particle is actually one order higher in comparison to that of diameter of particles which are required with air as the fluid. Okay, and this is the corresponding density value for different particles which are written over here. Then generally what will be happening while we are using the particle based measurements, for the case of gases, density of particle will be very high in comparison to the density of the fluid, so it will be greater than 1. Okay, now in this type of situation, what happens if we are having sudden fluctuations inside our velocity field, particles require certain time in order to respond to that velocity change. Okay, so generally what happens if we are having a single particle, so that actually requires exponential decay in order to adapt to the velocity change in the flow field which has actually occurred in a stepwise fashion. So what I am basically trying to say, for example, if you plot the velocity as function of space direction x, so you may find that initially you were having very large velocity and suddenly there is a change in the velocity, and velocity we are having some step change in the value of the velocity at some location, say xc. Now while our particle will be moving with the flow, so at this particular location particle will not be immediately coming into this flow field which is happening in actual practice. Rather particle will be showing some exponential decay towards achieving this value. Okay, so it means that the tracer particles are having some response time when we are having sudden fluctuations in our flow field to adapt to the flow situation. Okay, so the time scale of that sudden fluctuation or time scale the adaptation of that particular particle is actually given over here. So you can see this tau is nothing but 2 by 9 a square rho minus p divided by mu. So this is nothing but this refers to the time required for adapting the particle to sudden changes in the flow field. Okay. So while we are employing the particle based measurement techniques, we have to consider that the time resolution of our flow change should be larger in comparison to the response type of time of the particle. Okay, if it is lesser in comparison to the response time, then obviously we will be having some errors in our obtained velocity field. Okay, so that's what is written over here, that particle response time should be smaller than the smallest time scale of the flow. Then, while we are using the particle-based techniques, particularly for high-speed flow, where we are having the occurrence of nothing but shock waves. So, in this particular situation, what happens? Exact flow tracing can never be achieved. Okay. So, generally, what happens? Whatever the accuracy we get with the flow tracers, particularly in turbulent flow situation, that is quantified with the help of some parameter which is known as flow particle Stokes number. Okay, so particle Stokes number is a dimensionless parameter which is defined as the ratio between the tau. This tau refers to as nothing but the particle response time and the characteristic time at which our flow is actually flow field is changing. So this ratio particularly is known as Stokes number, and if the value of this Stokes number is less than 1, under such situations we can actually employ our particle based techniques. Okay, however, there are certain situations particularly where we are having the occurrence of shock waves. Under such conditions, exact flow tracing of particles can never be achieved. So let us try to see this with the help of this particular slide. So over here you can see this is nothing but a velocity contour which is basically obtained using the laser Doppler anemometry, and over here you can see this particular profile. So you can see there is a sharp change of velocity in this particular region. So this sharp change of velocity has actually reflected the occurrence of shock wave in this particular plane. Okay, so you can see on this corresponding graph, while the velocity is presented in normal direction, so this is considered as a direction normal to the direction of the shock. So when the velocity is presented over here in the non-dimensional format, so you can see this is the variation of the velocity. Okay, here it is written, this dashed line is actually showing the variation of the gas velocity. So you can see corresponding to the location S is equal to 0 mm, we are having nothing but sharp change in velocity of the flow field. Okay, now what has been done, different particles have been employed. So for example, you can see we have employed TiO2 solid particles which were having a particle diameter of 270 nanometers in order to measure our flow field. So you can see this particle is actually responding in an exponential fashion to the change in flow field. Okay, and this is also the measured velocity field we have obtained using the particle. So which is, so one time we have measured the velocity field with the space, and second time we have measured with time. Okay, so you can see over here along the abscissa, this particular bottom axis is actually referring to the space variation of velocity with space, and this top abscissa is referring to the variation of velocity field with time. So over here we are having time as unit along the microsecond. So you can see we have also fitted some of the curves over here in exponential fashion. So you can see this particular dotted line, black colored dotted line is nothing but exponential fit with space, and over here you are having the factor of exponential fit as -1 divided by 0.72, and with time actually the factor is -1 by 2.4. Okay, so you can see that when we are having this type of occurrence of the shock wave, then our particle based techniques will not be able to exactly mimic the flow field. Rather, we will be having some time lag in between the particle velocity and the flow field velocity. Okay. Then let us try to see what are the desirable characteristics of the particles which are required for measurement of velocity. So for the choice of shading particle, first thing is that there should be safety aspects. So our particles should not be toxic and hazardous. And apart from that, the particles should also not be corrosive and reactive to the fluid, whatever we are actually considering. Okay. Apart from that, these particles, whatever will be sitting inside our flow field, these should naturally evaporates. Okay, so if the particles are evaporating naturally, in that case, what will be happening? We will not be having any residue of the particle inside our fluid medium. Okay, so in that case, we will be getting nothing but less contamination of our fluid medium as well as the experimental facility. And at the same point of time, because what we have to do, we have to trace the motion of the particle. So we will be having certain optical window in our measurement system, which will be allowing the access to the particle. So that's why the particles should have characteristics that it is not actually contaminating our optical interface. Okay. Then now it comes the important consideration that we require certain particles while we have to do the measurement. Okay, so generally there are certain commercially available particles also, but particularly this type of commercially available particles are actually very expensive. Okay, so if we are having some closed loop system, here we can employ the commercially available particles. However, if we are having some situation where large amount of particles are required and our flow field is actually having the consideration of open loop circuit. So in that case, what will be happening? We cannot even take out the particles out of our fluid, and we cannot use these particles again. So we will be having the requirement of significant amount of particles. So under such circumstances, what is done? We may have certain system within our device itself in order to generate the particles. Okay. So generally, particles, we are having two types of generation system. One is either we have to take the solid particles as tracer, or we can have liquid particles as tracers. Okay. So in case of solid particles, we may allow polymers, hollow silicon oxide based micro balloons, or metallic coated spheres, which are generally quite complex to fabricate, but all these particles are nothing but commercially available. Then solid particles or powders are used to seed liquid flows or in applications such as combustion. Okay. So particularly the solid particles are required where we are having applications of high temperature, because if we are having high temperature and we are using liquid droplets as seeded particles, there may be the chances of evaporation of the droplets. Okay, so particularly we require solid particles under such circumstances. Okay, then it is always desired to have monodispersed size distribution and spherical shape of the particles. Why we want monodispersed? Because while we are tracing the motion of the particle, so we should have same type of flow dynamics. Okay, and at the same point of time, particles should be of spherical shape. So a spherical shape is some requirement which is actually which can be easily obtained, because while we will be using the particles, these will be of very small size, so their small size will be always ensuring the spherical shape. Then we should have particles which should naturally evaporate in order to leave minimum residue and introduce less contamination. Okay. Now this is some uh, device which is actually employed for generation of the aerosol particle. So you can see over here some gas is introduced from here. So this is nothing but an inert gas nitrogen. Then we are having some separator, because over here in this particular first chamber we are having some liquid also over here, and that liquid is normally some oil. Okay, and then while this air is introduced over here, this will be actually generating the large number of liquid droplets, which will be actually carried with the help of this separator, and then these liquid droplets will be dried inside some dryer, and then we will be measuring the flow rate of the liquid droplets, and we will be passing this through some saturator. Okay, so this particular saturator will be having some heating arrangement, and in this particular device, what basically we will be doing, we will be converting this liquid into saturated vapor. Okay, so while this saturated vapor will be entering inside the pipe or inside the flow field, actually we will be having immediate condensation of these vapors, and we will be actually getting liquid particles as our tracers. Okay, so this is one of the arrangement which is actually employed for generation of the aerosol particles. So in this particular device, actually what we are doing initially, while our particles are coming out of this heated chamber, we are having nothing but particles in the form of vapor, and while these are actually saturated vapor, and while this saturated vapor enters inside our flow field, this saturated vapor will be actually liquefying, and this will be actually converting into the liquid droplets, which will be acting as our tracer particle. Okay, then another type of arrangement which may be employed for generation of the solid particle is basically based on the atomization of the liquids. Okay, so in this particular arrangement, what we are having nothing but two nozzles. So in this one particular nozzle, we are having the flow of liquid. So from here, liquid will be coming out, and in this second nozzle, which is actually placed very close to the liquid nozzle, and it's in actually flow direction is normal to that of the direction of the liquid nozzle. So here what will be happening, we will be supplying certain amount of compressed air. So while the compressed air will be coming out of this nozzle, the velocity of the compressed air at this particular junction will be very high. Okay, so because of the high velocity over here, what will be happening, we will be having drop in the static pressure. Okay, so because of the drop of the static pressure, what will be happening, this liquid will be actually entrained inside this air, and we will be having the interaction between the fast moving gaseous phase with the liquid. So because of that, there will be the formation of large number of liquid droplets in our air jet. Okay, and these droplets then with the help of this outlet actually will be coming out. Okay, so over here you can see we are having this particular three different representation for determining the measuring the particle size distribution of the droplets. So over here you can see first refers to the diameter, mean diameter. So if mean diameter, a representative mean diameter is given over here as 5 micrometer, and then we are having shorter mean diameter, a representation of this is taken as 20 micrometer, and the rate at which droplets are generated is nothing but considered equivalent to that of 10 kilohertz. Okay, so if you see this particular photograph, so here you can see this is our x direction and this is our y direction, and this particular intersection is actually the origin. Okay, so over here this is our origin corresponding to this point, and then while we are actually measuring or changing the location of the nozzle, so this is nothing but x direction is referred to as shift in location of the air nozzle, and in y direction we are nothing but shifting the location of the water nozzle. Okay, so depending upon the shift in location, you can see we are getting the corresponding droplet size distribution. So it can be observed from these particular figures that the size distribution of the droplet is not being much influenced because of the change in location of the nozzles in the close proximity. Okay, however, if we vary the flow rate of the liquid and the flow rate of the gaseous phase over here, compressed air, these are actually the main important parameters which will be governing the size of the droplets. Okay, apart from that, while the droplets will be generating at this moment, we will be having a large spectrum of diameters of the droplets. So we may have very fine droplets and very large droplets also. So we require certain mechanical arrangement as a separator for removing the large droplets out of the stream which will be coming out of this particular outlet over here. Okay, so this type of particular atomizer is referred to as twin fluid atomizer, which is required for generation of the liquid seeded particles. Then another type of device is shown over here. So in this particular device is also based on the principle of atomization for generation of the droplet. So over here you can see nothing but we are having a pool of oil, and inside this pool of oil we are having different Laskin nozzles, and then along with these nozzles you can see this particular section is actually zoomed over here, and zoomed view is shown over here. So over here you can see that the air is coming out of this nozzle, and then we are having some collar which is having very fine diameter over here, and just beneath the collar we are having number of outlets, multiple outlets across the periphery of this nozzle. So while air will be coming out of this nozzle, it will be leading to the formation of large number of small liquid droplets. Then we are having one impactor plate over here. So this particular impactor plate will be actually catching all the larger size droplets, and whatever the fine size droplets we will be having, these will be actually passing through this annular section, and finally these will be coming out and can be then inserted inside our flow field. Okay. Then whatever till now we have seen the different type of arrangements for obtaining the liquid type seeded particles. These particular arrangements are based on the principle of mechanical atomization of the liquid particles. Okay, so these particular type of arrangements are nothing but leads to generation of droplets which are of varying sizes. Okay, but in many of the applications what we require nothing but monodispersed droplets. Okay, so particularly for obtaining the monodispersed droplets, we nothing but we require one fluidic principle which is based on the formulation of Rayleigh jet. Okay, so what we are having over here, we are having nothing but d as diameter of the nozzle, out of which some jet is coming out. Okay, and in this particular jet, if we are having pulsed flow situation, if we are generating some sort of pulse, because of that what we will be having, we will be having the generation of interfacial waves over the surface of this jet. Okay, now if over here you see lambda as the wavelength of these interfacial disturbances which are appearing on the periphery or on the surface of the jet. If this wavelength is in the range of 3.5 times d to 7 times of d, in this particular region we will be nothing but having the unstable regime, and particularly when the wavelength will be becoming identical to that of 4.508 times of diameter, at that time we will be having complete unstable situation, and we will be having the pinch off of droplet. Okay, so this particular neck which has formed over here, this will be narrowing down, and it will be finally resulting in formation of a droplet which will be coming out of the continuous jet structure. Okay, so diameter of this particular droplet particle is nothing but cube root of 6 times v dot divided by pi into f, where this v dot is nothing but the flow rate of liquid. Okay, so this is nothing but the rate at which liquid is coming through this nozzle, and this f refers to the frequency of disturbance. Okay, so f refers to as the frequency of disturbance. Now disturbance can be obtained using two means. So one of the way for obtaining the disturbance is that instead of giving a constant flow rate over here, we may supply some pulsating flow rate. So we will be giving some pulse in our flow rate, which will be actually leading to the formation of interfacial waves. Okay, and another mechanism could be that we may have some mechanical arrangement which will be generating some periodic pulses, and because of that we will be actually getting the occurrence of interfacial waves over here. And when the amplitude wavelength of the waves will be becoming 4.5 times of diameter of our nozzle, at that time we will be having pinch off. Okay, so this is one of the finest way of obtaining monodispersed droplets. Okay, so over here we have included one mechanical arrangement which may be employed for generation of the droplets using this principle. So you can see that we are having some inlet through which we are allowing the liquid to flow. Then at this particular bottom section we are having nothing but a orifice plate. Okay, and this particular orifice plate is actually connected to a piezoelectric transducer, and in this piezoelectric transducer we are providing some excitation signal, and F we will be considering as nothing but our frequency of the excitation signal. So because of that, we will be having the oscillations of this orifice plate, and while the fluid will be coming out from here, we will be having nothing but generation of the waves along the periphery of the liquid surface. Okay, and from this particular inlet, we are introducing the carrier gas, which will be actually passing through this orifice plate, and it will be actually carrying all the droplets which will be producing at this particular orifice plate. Okay, so this is a mechanical arrangement which may be employed for the generation of the mono dispersed droplet distribution. But the only disadvantage of this type of system is that over here we will be having the generation of droplet at very low frequency. Okay, so we will not be having sufficient population of the droplet in order to obtain our entire in order to resolve our entire flow field. Okay, so we may have to install multiple arrangements in parallel in order to obtain the desired amount of the droplets. Then apart from the generation of the liquid particles, we may have the generation of solid particles as well. Okay, so for the solid particles also, we may use either the principle of atomization. Okay, so when we are using the principle of atomization, so in that case, what we will be doing, we will be considering some liquid suspensions, and then we will be allowing the liquid part or solvent part of that suspension to evaporate, which will be finally leaving a solid particle. Okay, so nothing but atomization, we can atomize that liquid suspension using any of the means which is described in the previous slide. But what we will be doing actually the suspension of liquids, and then this will be having characteristic in such a way so that the liquid and solvent will be evaporating, and finally we will be getting solid particles. Okay, so latex particles are generally employed with the very narrow size distributions in order to obtain such particles, and the suspensions what we will be considering, these must be dilute enough before atomization. Why? So that whenever we are obtaining the particles, solid particles, so inside the solid particle, if we have only one latex, okay, if our concentration is more, then we may find that we may have more than one latex particle inside our final solid droplet which will be generating. Okay, so for that, generally what is done, we actually first dilute our suspensions in order to ensure this particular condition. Then apart from that, we may go for the another different type of solid particles, for example TiO2 and ZrO2 in mixture of 5% ethylene glycol in order to obtain such type of solid particles. Okay, then another method for introducing the solid particles into our flow field is basically using the powdered solid particles. Okay, so we may have powder solid particles. So for example, one of the depiction of rotary brush seeder is shown over here. So what we are having some piston cylinder arrangement, and inside that piston cylinder arrangement we are having large number of solid particles, and these solid particles are nothing but in the powdered form, and then we are having some piston cylinder device which is actually providing the feed, and this is feeding the solid particles to certain device, and in this particular device we are having some rotating brush. Okay, so what it will be doing, this rotating brush will be taking some of the particles, and while it will be carrying from this particular location like this, and it will be continuously feeding all the particles into our flow pipeline. So from this particular side you can see our flow of compressed air is actually happening. Okay, in this particular type of arrangement, the density, or I should say the concentration at which the solid particles are loaded inside this particular pipeline, that depends upon the rate at which this piston is actually moved and the rate at which our brush is rotating. And at the same point of time, the flow rate of the compressed air can also control the concentration of the solid particles. Okay. So typically when we are using the powders, quartz dust and calcium glass spheres or titanium oxide are mainly used as seeded particle. Now one of the advantages over here of using the compressed air is that because if we are using the compressed air at high velocity, it will be actually avoiding the coagulation between the powdered solid particles. Then another arrangement which may be employed with the powdered particles is nothing but a cyclone aerosol generator. So in this, what we are having the solid particles. Then we are allowing some gas to enter tangentially inside this cyclone. Now, while gas will be having some spiral motion, it will be carrying the particles along with it, and some of the particles will be moving through the outlet, and this will be actually suspended in our gas. So this particular type of arrangement is useful for producing the particles in the range of zero point 0.1 to 1 micrometer. So generally Al2O3 particles are actually used with this type of arrangement. And cyclones also acts as the size separator along with the method for dispersing the particles. Why? Because while gas will be undergoing this tangential motion, so we will be having actually separation of the particles because of the centrifugal action. Okay, so the only particles which will be having almost mono dispersed size distribution, these will be only coming out through this particular outlet. Okay, because whatever the bigger size particles we will be having inside our flow field, because of their weight, they will be moving in outward direction, and after striking with the surface of the cyclone, they will be actually falling in the downward direction. Now, these are some of the different type of solid materials and their corresponding density, refraction index, and melting point, which are commonly used as seeded particles. Okay. Then sometimes what we do, because particularly we have to actually acquire the light signal from the particles once we have incidented some laser light on this due to the scattering effect. So we sometimes coat the particles with some fluorescent dyes in order to improve their output signal capacity. Okay, so these are the different types of dyes which are normally employed, fluorescent dyes which are normally employed to coat the particles, and these are their corresponding optical characteristics. Okay, then it is very important to seed the particles in some optical concentration. Okay, so while we are seeding the particles, neither they should be below some optimal concentration, because if our concentration of the particles is small, in that case we will not be having good spatial resolution. However, if the particles are too much dense inside our flow field, that also will not improve the accuracy of velocity measurement. Okay, so I have highlighted over here the two different situations. So one of the situation is corresponding to the homogeneous seeding, and another is corresponding to inhomogeneous seeding. Okay, so in first case you can see we are having nothing but a square cylinder as bluff body, and across this square cylinder we are having nothing but flow of fluid. Okay, and in this particular fluid flow we have seeded a large number of particles inside our flow field. So over here you can see this is a typical photograph of the flow field. So from this photograph you can see that particles are almost homogeneously distributed inside the entire flow field. Okay, then this is a second situation where we are having some nozzle, and out of this nozzle we are having a jet which is actually coming out. Okay, and what we can see over here, this jet is nothing but having lot of turbulence. So because of the turbulence we will be having significant amount of circulation. So you can see these particular areas over here we are having some circulation. Okay, so now because of the circulation effect, what will be happening due to the centrifugal action, particles will be moving away from the core of the rotation. Okay, so we are having some of the patch where we are not having any particle inside our flow field, and we are having certain portions where we are having very densely spaced particles. Okay, so this type of inhomogeneous distribution will be coming into picture where we are having the turbulent and very chaotic flow situations. Okay, but generally in order to obtain the accurate flow field, we should have some optimal loading of the particles inside our flow field, and our particles should have homogeneous distribution inside the flow field. Then now based on this particle techniques, we may employ different techniques. For example, particle image velocimetry, laser Doppler anemometer. We may employ molecular tracing velocimetry, or we may employ even Doppler global velocimetry. So what we will be doing in this particular lecture, I will now discuss first about laser Doppler anemometer, and then in our next lecture we will have discussion on the particle image velocimetry. Okay. So laser Doppler anemometer, basically this is considered under the category of non-intrusive particle velocimetry. Why? Because I have already explained you in the first slide, because we are having very small particles which are actually neutral, buoyancy neutral, and these are not affecting our flow field. Okay. Then one of the disadvantage of hot wire anemometry is that in case of hot wire anemometry, we can determine the magnitude of the velocity field. However, we cannot determine its direction. Okay. For example, if I consider a hot wire sensor over here, and my flow is taking place from left to right and with some velocity u, and now I take another situation, that same sensor I am having, and flow is actually taking place from right to left with the same amount of velocity u. Okay, so in both these situations, we will be having the same thermal characteristics we will be obtaining from this, particularly for this heated wire sensor. So because of that, we will not be able to determine the directional dependence. Okay, we can determine the magnitude of the flow velocity, but we cannot determine its direction. So that's why this is one of the disadvantage of hot wire anemometry. So particularly that disadvantage or that limitation can be avoided by the use of laser Doppler anemometer. Okay, so here we are having the sensitivity of direction also. Then we get high spatial and temporal resolution, because that is something which will be depending upon the loading of the particles. Okay, and then we are having over here very high accuracy. So particularly this laser Doppler anemometer is based on the principle of Doppler's effect. So for example, you can see over here we are having a laser, and from this laser we are sending some signal in this particular direction EB. So EB refers to as nothing but unit vector. Okay, and B is referred to as the B is referring to the incident beam. Okay, and you can see lambda V is the wavelength of the incident beam, and this particular incident beam is actually interacting with the particle. And once it will be interacting with the particle, actually particle, because particle is moving at certain velocity Vp, so there will be some change in frequency of this incident signal. So we will be having phase shift in its frequency. So after that, what will be happening? We will be getting some signal which will be coming out of this particle, and that signal then we will be actually detecting at some receiver unit. Okay, so EPR is nothing but refers to as the direction from the particle to the receiver side, and we are having this nu s as our angle over here, which is between the receiver and the z-axis. Okay, and this is our x-axis over here. So particularly we can see that whatever the frequency we will be getting at the receiver, that will be nothing but Fv times 1 minus Vp, where Vp is velocity of particle and Eb refers to the direction unit vector in incident beam direction. Okay, divided by C, where C is nothing but velocity of light, particularly this speed of light we will be having in our fluid medium. So outside this particle we will be having certain fluid medium. Okay, because these particles are nothing but seated inside some fluid medium. So C is velocity or speed of light in fluid medium, divided by 1 minus velocity of particle, and that velocity of particle now we will be taking in this particular direction, divided by C. So this is nothing but this represents the change in frequency, and this further can be approximated as Fv plus Vp times EPR minus Eb divided by lambda. Okay, so over here you can see this Fb is nothing but the frequency of the incident beam, and then whatever the frequency we are receiving, that is nothing but we are having some term over here, and this frequency is changing by this magnitude. Okay, so this particular term over here is nothing but accounting for the frequency shift in the signal, and this frequency shift in the signal is basically, you can see over here, is nothing but proportional to the particle velocity and the difference of the unit vector in the direction from particle to receiver and this is the direction of the incident beam. Okay, so this is actually, this second term is nothing but represents the frequency shift, and this frequency shift is having linear dependence on the velocity of the particle. Okay, so this type of particular formulation is applicable for particle velocities very small in comparison to the speed of light, and speed of light particularly for incident beam in the fluid medium will be equal to nothing but frequency of the beam multiplied by wavelength of the beam. So Doppler's shift, whatever we will be obtaining over here, this particular shift, this is nothing but is of the order of 1 to 100 megahertz, which is in comparison to the frequency of the laser light is actually very, very small. So whatever the light we are incidenting over here, its frequency is approximately of the order of 10 to power 14 megahertz, whereas whatever the shift we are getting in the frequency, that is very, very small, 1 to 100 megahertz. Okay, so this type of very small shift in the frequency is actually very difficult to measure, and it will be impossible to resolve. So because of that, generally in the practical scenarios we don't go for the single incident beam, rather we use the dual incident beam as measurement device in our practical applications. Okay, so let us try to see. In case of dual beam configuration, what we are having nothing but two laser beams. So you can see over here, this two laser beams are coming in direction E1 and E2, and let us consider lambda 1 and F1, and lambda 2 and F2 are the corresponding wavelength and frequency. Okay, Vp is the velocity of the particle, and finally we have placed some receiver over here, and this receiver is actually representing the direction EPR from particle to the receiver. Okay, so over here you can see the corresponding angles are also marked. So this theta is over here referring to as the incident waves angle, and then this particle is actually making angle alpha with the x direction. So where x is nothing but referred to as the normal direction to that of the particle or to that of the incident beams. Then we have in this particular section where we will be having the interaction between the two beams. This particular section is nothing but our measurement volume. Now in this particular measurement volume, our particle will be actually passing through this measurement volume, and then uh, we will be having some scattering of light. Okay, so we are considering that E1 and E2 are the directions in which our light waves are actually initially incident. Okay, and then finally in this particular direction we are actually locating our receiver. Okay, so if you see over here, we will be having this n normal direction. This will be nothing but equal to E1 minus E2, and in terms of angle, if you try to find out over here, because if this angle is theta, then obviously this angle over here also will be equal to nothing but theta. So finally we will be finding, and if Ex, if in this particular x direction we consider that our unit vector is nothing but Ex, so finally we will be finding this n over here, this normal direction is nothing but equal to E1 minus E2 equal to 2 sine theta divided by 2 into Ex. Okay, so here what we are having, the frequency of the first incident wave is nothing but equal to frequency of incident beam plus Vp EPR minus E1 by lambda V. Then corresponding the second frequency, whatever we will be getting after the shift in the frequency, Doppler shift in the frequency, that will be nothing but Vp times EPR minus E2 divided by lambda V. So finally, if we take the difference of these two frequencies, F1 minus F2, so that is nothing but our main signal which will be detected. So we will be finally basically detecting the difference of the two frequencies. Okay, so we will be finding that as nothing but Vp times E1 minus E2 divided by lambda V. Okay, and particularly we have seen that E1 minus E2 I can write as nothing but, from this vector diagram I can write as 2 times sine theta by 2 divided by lambda V. Okay, and for this Vp also I can write magnitude of Vp into cos alpha. Okay, and because we have to now take this in the direction of the detector. Okay, now you can see over here this Vp magnitude into cos alpha is nothing but, this angle is our alpha, so Vp cos alpha is velocity in the x direction, and x is referring to the normal direction from the plane of incidence of beams. Okay, so I am writing this as Vp in the velocity in the perpendicular direction. Okay, so it means the change of frequency is nothing but having direct dependence on the velocity. This particular point can also be seen with the help of interference pattern, whatever we will be getting, because what we are doing, we are incidenting the light from two different sources. So obviously, while these two different light from the two different sources will be having interference, so we will be having sometimes the wave fronts will be having construction fringes, and sometimes we will be having the destructive type fringes. Okay, so we will be getting some fringe like patterns over here. So you can see the width of each fringe will be equal to lambda b divided by 2 times sine theta by 2. So this type of fringe patterns we will be getting, and in this particular fringe pattern, what will be happening, our particles will be actually interfering with the fringes, and we will be getting some final frequency, output frequency signals. Okay, so one of the depiction is given over here. So over here you can see this abscissa is actually marking the velocity of the particle. So over here we are having some if we are having the zero velocity of the particle, corresponding to that we will be nothing but getting our frequency value identical to that of the kind of fringe we are having, whether we are having constructive fringe or we are having the destructive fringe. Okay, now if we consider that we are having two particles, Vp A and particle B, so one is moving with velocity of particle as A and one is moving with velocity of particle B. Now if we consider that both the particles are moving in opposite direction, so one is moving in downward direction, one is moving in the upward direction. Okay, and so what we are getting, nothing but one side we will be having positive velocity and one side we will be having negative velocity. But in this particular arrangement, what finally we will be getting, because while it will be, this particle will be interacting with the fringe, now depending upon the velocity of the particle we will be having some output shift in the frequency. Now if we measure that output shift in the frequency, if we consider that the velocity of both the particles is same, we will be finding one that both are giving us nothing but same amount of velocity. Okay, so it means that if we employ this particular arrangement, so once again we are not able to determine the direction of the flow. Now in order to make it compatible to measure the direction of the flow also, what we can do, we can initially have some shift in frequency. Okay, so for example, corresponding to zero velocity of the particle, initially our velocity frequency was 0. So now what we have done, we have actually incidented the beams at some different frequencies. For example, if my f2 is one frequency and f1 is one another frequency, so I am considering f1 as nothing but f2 plus fs. Okay, so now because of the difference in frequency of the two incident beams, what we will be having, we will be having some moving fringe pattern. So because of the moving fringe pattern, what will be happening, if we are having some particle at rest, and while that particle at rest will be actually moving, interacting with the moving fringe pattern, so we will be getting corresponding to zero velocity as the whatever the initial shift we have provided in the frequency, that we will be getting as our output frequency. Okay, corresponding to the zero velocity of the particle. However, if we consider the motion of the particle, then this particle will be now interacting with the moving fringe pattern. So depending upon if it is approaching towards the moving fringe or if it is moving away from the moving fringe, we will be having actually difference in the output frequency. So for example, in case of a particle, we may consider that particle is approaching towards the fringe. So because of that, we are getting highest frequency, and in case of particle which is moving away from the fringe motion, we are having actually decrease in the frequency signal. Okay, so in order to make this laser Doppler anemometry compatible for determining the direction of the flow, what we have to do, whatever the initial two waves we are considering, we have to initially take some frequency shift in between the incident beams, so that we are getting some moving fringe pattern, and then we can determine the interaction of the particle with the moving fringe pattern in order to obtain the directional dependence of velocity. Okay, then this is one representation I have shown over here. So this is nothing but the typical signal we can which we can observe in the measurement volume. So you can see at different locations, particularly near the interference zone, we will be having significant amplitude of the output signal, and as we will be moving away from the zone, we will be having actually a decrease in amplitude of the signal. Okay, so that is something, it's actually a typical representation of the signal whatever we will be obtaining because of the interaction of the two incident light waves. Okay, now I will stop at this point, and we will discuss about more particle based measurement techniques in our next lecture. Okay.